Hello everyone. So in this session, we are going to deeply understand one of the most important evolutions in artificial intelligence history. We will go step by step through the complete journey from like traditional neural networks to recurrent neural networks, and then LSTMs, then attention mechanisms, transformers, large language models, and finally modern AI agents. So this evolution is extremely important because modern systems like GPT-4, Claude, Gemini, ChatGPT, and autonomous AI agents all are like built on top of these breakthroughs. So this is not just a theory. This is the foundation of modern AI. By the end of this session, you will understand why RNNs were created, why they failed, how attention changed everything, why transformers became dominant, and how modern AI systems evolved into intelligent agents. Let's begin. See, before sequence models. So before recurrent neural networks existed, most AI systems used something called feed forward neural networks. These networks worked very well for static problems like image classifications, numerical predictions, and tabular datasets. But they had one major limitations. They treated every input independently. Say, for example, if you give this sentence, I grew up in France, so I speak fluent, right? So the model needs to remember the earlier word France to predict the word called French. So traditional feed forward networks could not do this because they had no memory. Every input was processed independently. Language, however, is a sequential. The meaning of a word depends on the previous words. So this became the motivations for recurrent neural networks. So I hope this is pretty clear to everyone. Now let me quickly move to another slides. So as you can see here, introductions to RNNs. So researchers that time, right, introduced this recurrent neural networks, or we say RNNs. So instead of processing words independently, RNNs introduced something called a hidden state. The hidden state carries information forward through time. At every step, the model takes the current step plus the previous hidden state and produces a new hidden state. This allows the network to remember earlier information. For example, like see, I love deep learning. The hidden state evolves step by step as a sentence progresses. This was revolutionary because now AI system could process this language, speech, time series data, and sequential informations. So RNNs were one of the first major breakthrough in sequence learning. Let me move to next slide. So how RNN training works. Now let's understand how RNN actually learn. RNNs are trained using a process called backpropagation through time, also known as BPTT, backpropagation through time. During the forward pass, token move through the network hidden state are updated and predictions are generated. Then during backpropagation, right, errors flow backward through all the time steps and gradient updates the model weights. This allows the network to learn pattern across these sequences. However, this introduces a massive problem. As a sequence became longer, these gradients became unstable. This led to a vanishing gradient problem. So let's discuss about this vanishing gradient problem. This was one of the biggest challenge in the deep learning. Imagine a long sentence. To understand the final word, the model may need to remember information from many steps earlier. But during training, gradient repeatedly multiply through many layers and time steps. As this happens, the gradients become smaller and smaller Eventually they approach zero. When this happens, the model effectively forgets earlier informations. This is called the vanishing gradient problems. So as a result, this RNN struggles with long-term dependencies. They could remember short context but failed on long sequences. Researchers needed a better memory mechanisms. That led to the LSTMs. So LSTM architecture, let's discuss. LSTM stands for this long short-term memory. LSTMs were designed specifically to solve forgetting. The core innovation was gated memory. Instead of blindly updating memory, LSTMs introduced gates that controls information flows. There are three major gates they have added. First is the forget gate. This decides what information should be discarded. And second is the input gate. This determines what new information should enter the memory. And third was like the output gate. This decides what information should be exposed to the next step. LSTMs also introduced something called a cell state. This acts as a persistent memory highway across long sequences. This architecture dramatically improved the long-term memory retention. Why LSTMs were revolutionary? LSTMs became extremely successful. For years they dominated natural language processings. They powered machine translations, speech recognitions, conversational systems, and sequence predictions. Google translates, these are heavily relied on LSTMs before transformers, were invented. So LSTMs solved many memory problems, but one major issue still remained. So sequential processing. Even though memory improved, training was still slow. So you are getting right. Training was still slow. So let's discuss of this GRU network now. So researcher later then they introduced GRU, gated recurrent units. So GRU simplified these LSTMs. They used fewer gates and had fewer parameters and trained faster. In many applications, GRUs achieved a performance similar to LSTMs. So basically this made them attractive for lightweight systems, mobile AI and smaller NLP models and all. But despite these improvements, both LSTMs and GRUs still suffered from the same fundamental limitations: sequential execution. So let's discuss on this sequential bottleneck. This became the major challenge. RNNs, LSTMs, and GRUs process tokens one by one. Word 1, then word 2, and then word 3, and then word 4, so on. So this means computations cannot be parallelized efficiently. GPUs are designed for massive parallel operations, but sequential models blocks these parallelisms. This made training very slow, difficult to scale, and inefficient for large datasets. Researchers needed a new approach. Instead of passing information step by step, what if every token could directly look at every other token? That idea became attention. Then attention mechanisms came. Let's discuss about these attention mechanisms. Attention changed deep learning forever. So the core idea is simple but very powerful. Instead of compressing everything into one hidden state, token dynamically focus on relevant informations. So attention uses three concepts: query, key, and value. QKV, query, key, and value. A token asks what information am I looking for? So this is basically a query. Other tokens advertise what information do I contain. Those are keys. The actual information passed forward becomes the values. The model then calculates attention scores between the tokens. Then it combines information based on the importance. This allows dynamic contextual understanding. Now, let's see this attention example. Let's see means why this attention is powerful. Take a sequence like the animal didn't cross the road because it was tired. The word it refers to an animal. Traditional RNN struggles because information had to travel across many sequential steps. But attention allows this token it to directly focus on animal. No long memory chain required. This removed this whatever bottleneck of our compressed hidden states. So this was a massive breakthrough. Now transformer revolutions. So in 2017, researchers published one of the most important paper in the AI history. Attention is all you need. This introduced the transformer architecture. The revolutionary idea was remove recurrence completely. No RNNs, no LSTMs, only attention. So transformer process all tokens simultaneously. This enables massive GPU parallelism. Training speed improved dramatically and models could finally scale to billions of parameters. This was the beginning of the LLMs, large language model era. So transformer components, let's see what all it has. Let's understand these transformer components first. So first you see this tokens are converted into embeddings. Embeddings are numerical vectors, representations of the words, as you know already. So then positional encodings adds a sequence order information. Because transformations process everything in a parallel, they need explicit position awareness. Then this self-attention learns relationship between tokens. Multi-head attention allows this model to learn multiple relationship types simultaneously. Feed forward layer, this defines the representations further. And residual connections and layer normalization stabilize deep learning. Together, these components created an extremely scalable architecture. Let me move to next slide. Self-attention deep dive, basically. So self-attention is the heart of the transformer. Okay. So every token compares itself with every other token. This produces contextual understandings. The process works like this. First, token generates query and then key and values vectors. So then similarity scores are computed. Okay. So softmax normalizations converts scores into probabilities. Finally, weighted information gets combined into the contextual embeddings. And this allows tokens to dynamically understand meaning based on context. This is why transformations become so powerful. Let's look into this multi-head attention. So transformers uses multi-attention heads simultaneously. Each head specializes in a different pattern. One head may learn grammar, another may learn semantic meaning, and another may focus on, say, long range dependencies, and another may capture syntax. So this parallel relationships learning creates a very rich representations. Multi-head attention is one reason transformers output performs older architecture. Let me move to another slides. Encoders versus decoders. Transformers can use encoders, decoders, or both. So encoders specialized in understanding. They are excellent for embeddings, semantic search, retrievals, and classifications. BERT, if you have heard BERT model, right? BERT, B-E-R-T, BERT is the encoder based. Decoders specialized in generation. They predict the next token repeatedly. GPT models are decoder only architectures. Just keep in mind, okay? GPT models are decoder only architectures. Encoder decoder system combine both understanding and generation. So these are common in translations and summarization systems. Let me move to next slide. GPT architectures. So GPT simplified transformers dramatically. It uses decoder only architectures. The training objectives is surprisingly simple. Predict the next token, that's it. But when trained at massive scale on the internet sized kind of data sets, something remarkable can happen. So the model developed reasoning, coding, language understanding, planning, and generalizations abilities also. So these are called emergent capabilities. Scale transform simple next token predictions into a high capable intelligence systems. Now emergent capabilities. So large transformers began exhibits abilities researchers did not explicitly program. These includes reasoning, code generation, chain of thoughts, planning, tool usage, and even agentic behaviors. This surprised the AI community actually. It showed that scaling transformers could create a generalized intelligence-like capabilities. This led directly to modern AI assistants and autonomous agents. So modern AI agent stack, let's discuss. Today AI systems are much more than just transformers. Modern agents combines these transformers, memory systems, retrieval pipelines, tools, planning engines, and orchestrations frameworks. For example, if I have to take like LangGraph, PUAI, AutoGen, MEMGPT, these systems supports persistence memories, autonomous like executions, tool usage, and long running workflows. This is the current frontier of the AI engineering. Now, let's complete evolution summary. We can see feed forward neural networks solved the static learning. Okay. And RNN introduced a sequence memory. Okay. And LSTM solved long-term forgetting issue. Then GRUs improved its efficiency. And attention removed memory bottlenecks. And transformers enabled massive scalability. And LLMs demonstrated emergent intelligence. And AI agents combined models with memory, tools, and workflows. The entire evolutions can almost be summarized as, if I can say, better ways to manage the relationship and memory across tokens. That's the core story behind the modern AI. Thank you. Thanks, everyone.